I am amazed every time I walk through a Costco and I see the quantity of food that we're able to make in practice. And I thought it'd be cool to make a video that would describe the kind of models that a chemical engineer would be working with to uh, manufacture food. And one unit, a food processing chemical engineer, would most likely come into work with would be a dryer. And to start off with, a dryer we can draw pretty simply as just a basic unit, and then we'll have an inlet stream of some kind of, we'll say it's a fruit dryer, and so we'll have some kind of wet fruit coming in, and we'll have dry fruit leaving, or drier fruit, and we'll have an inlet stream of hot air and a stream of call it colder air. So the air will dry the fruit and absorb the water. So this will be colder air. And the way a chemical engineer would approach this problem is by coupling an enthalpy balance with a mass balance. And an enthalpy balance would involve the following. So if we write this out, so a question that would probably lead us to want to model the system would be what kind of constraints, if we wanted to know, if we wanted to process 100 kilograms per hour of fruit, what kind of flow rate of air are we going to need to do that? This is how we would do it. So the enthalpy balance would tell us that in this symbol, HY, enthalpy in of the air, so this is the specific enthalpy in of the air, times the mass flow rate of dry air in, plus the enthalpy in of the fruit times the mass flow rate of the fruit, must be equal to the enthalpy leaving our system, so HY out of the air times the mass flow rate of the air, dry air, out, plus the enthalpy leaving our system in the drier fruit times the mass flow rate of the dry fruit. And the reason we can make this equation is because we are saying that energy is conserved. So this is just another way of saying that the enthalpy in has to be equal to the enthalpy out. Another thing to note for later on is that because we are going to assume we have no accumulation of mass, we can say that the mass flow rate of dry air in must equal the mass flow rate of dry air out. So I will let this term simply be equal to mdA. And the same can be said for the mass flow rate of fruit. And so the next step that we're going to do is look at these enthalpy terms for our air and for our fruit. And so if we examine the enthalpy in of our air, it will have two contributors. It will have a term referred to as the specific enthalpy of the air, CS. This is a per mass basis, and this is a function of humidity times, and then we're going to have some temperature in of our air, minus, and then a reference temperature, which I will call 0 degrees C for the sake of simplicity. And so as long as we keep our reference temperature of 0 degrees C the same throughout our problem, we won't have any issues. The other contributor to our air's enthalpy is something is the enthalpy contained in the water that is present. And so the way we measure that is also influenced by the humidity of our inlet airstream. And so that will have a value of plus lambda times the inlet humidity of our air. And just to clarify these terms, so CS is a term that we can define as 1.005, this is a textbook definition, plus 1.88 times the humidity of our airstream. And this value is called the latent heat of vaporization, and lambda is a function of temperature. And to assign a numerical value to it, it's a tabulated value, so we would commonly just look this up in a book. Lambda at 120 degrees centigrade is equal to 2200 kilojoules per kilogram, and this is of water. And so to recall the units that we are working with, HN will have units of kilograms of water per kilogram of dry air. And so the kilograms of water in the denominator here will cancel out. So this HYN term as a whole will have units of kilojoules per kilogram of dry air. And so the reason psychrometric charts are important is because we're going to need to be able to figure out what these HN terms are to actually evaluate what our enthalpy is for our air inlet stream. Okay, so what I'm going to do now is just box the definition that we have just found for the enthalpy that is present in the airstream, so we can apply the same relationship to the air in our outlet stream by simply switching the air in with the air out term. So we would use T out air here, as well as the outlet humidity value to evaluate our outlet enthalpy value of our airstream in the dry air above. Now, to examine the enthalpy of the fruit that we are drying, or whatever food we're interested in, the terms will be a little bit different, but it will still have the same two terms. So if we examine HYN of our fruit, what we will note is that the physical dry fruit itself will have some kind of specific heat capacity that I will refer to as CF, and that will have, we'll need to multiply this by the inlet temperature of the food minus 0 degrees C, because it's our reference temperature and we're keeping that consistent. And then we will add to this term the relative humidity, or what we are going to take into account the moisture content in our fruit, and consequently that water that is present will have its own enthalpy contribution to the total enthalpy of our fruit. And so the way we'll do that is we will, on a psychrometric chart, figure out what the relative humidity is of our fruit, and I'll call that RH, and RH will be a value between 0 and 1. It's a percentage of how far you are to saturation, and so you'll have relative humidity of the fruit divided by 1 minus relative humidity of the fruit. And this term here will have units of kilograms of water per kilogram of fruit. And I encourage you to do the dimensional analysis on this and verify this. And so because we now have units of kilograms of water, we're taking into account the enthalpy contribution of water, we will multiply this by the specific heat of water, Cw, and we will also multiply this by the temperature of this fruit stream, T in fruit, minus 0 degrees C. So I will now box this equation. And with these terms, the enthalpy of our fruit and of our air, we can do the same for our outlet terms. The other thing to note here is that this value of lambda may take on a different value, because if our air exiting our dryer is at a different temperature, we will need to evaluate a new latent heat of vaporization term and look that tabulated value up. So if we now go back up to our equation, our overall enthalpy balance equation, we will plug in all of these quantities that we've just derived, and now perform a mass balance on the water. And because we know that we are not creating or destroying any mass in our system, we can say that the mass balance will tell us that the water in must equal the water out. And so putting this into mathematical notation, what we would have is that if we had the mass flow rate of the dry air times the inlet humidity of the dry air plus the mass flow rate of our fruit times the relative humidity of our fruit divided by 1 minus the relative humidity of the fruit, and this will be in. This term, this side must be equal to the mass flow of the dry air exiting our system times the humidity of that exiting airstream plus the mass flow of the fruit times the relative humidity of the fruit leaving our system divided by 1 minus relative humidity out. And so if we do a dimensional analysis on these quantities, because this HN term is absolute humidity, this will have units of kilograms of dry air per hour, let's say, and we're going to be multiplying this by kilograms of water per kilogram of dry air, and so this makes sense. And then the same goes for this term here. If we do dimensional analysis on it, what we find is that we would have the mass flow of fruit, so we would have kilograms of fruit per hour, and then this side of the equation will have units of kilograms of water per kilograms of fruit. And so the total mass balance will have units of kilograms of water per hour, which is what we'd expect. And so all the dimensions agree on both sides. And so I will now box this equation. So this mass balance equation will be another key equation needed by chemical engineers to actually evaluate this system. And in practice, at this point, what would happen is a chemical engineer will evaluate these two systems. So I'll call this mass balance star, and our total enthalpy balance I'll call star prime. And so if we evaluate star and star prime, we can solve for whatever mass flow rate will be required of our airstream to figure out what we need to successfully dry our fruit to a needed level. So I hope you guys found this useful, and let me know if you have any questions. I just finished writing this, but we can find what we need simultaneously. Okay, so that's it. Thanks for watching, and